The conductance is due to all the ions which has been produced by dissolving only 1 mole of an electrolyte. That is known as molar conductivity. Ions which has been produced from that 1 gram of electrolyte, so that will be responsible for conducting the electricity. Hence it is known as equivalent conductivity. Conductivity of an electrolytic solution and infinite solution is known as limiting molar conductivity. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were discussing with the unit called electrochemistry. Under that, we have studied about the conductivity of a electrolytic solution. Under that, we have understood that what is resistance, and also we have understood about the resistivity, and also we have learnt about the cell constant and conductance and the conductivity, and also we have solved a few problems, right? Today we'll move on to the next topic of this unit: molar conductivity, equivalence conductivity, factors which affects to the conductivity, and we will discuss what is Koch-law and applications of the Koch-law. Okay? So first I'll directly move on to the molar conductivity. Already we have understood that conductivity, what does it mean? So conductivity means what? The conductance means it is the ability of a substances to conduct the electricity, right? And also we have understood that conductivity, which is nothing but a reciprocal of a resistivity, right? And today we are dealing with the molar conductivity. Let's see what is the molar conductivity. Molar conductivity of a solution at a given concentration can be defined as a conductance is due to all the ions which has been produced from 1 mole of electrolyte which has been dissolved in an solvent. This is known as molar conductivity. For example, if you consider a container, okay, which consists of a electrode, which one will be act like a cathode, another one will be act like a anode, and we have connected these two electrode to the battery or to the electrical current. And remember, the molar conductivity means we are dissolving the 1 mole of an electrolyte. So we are dissolving 1 mole of electrolyte. 1 mole of electrolyte. So how much of the ions which has been produced from this 1 mole of an electrolyte, that is said to be a molar conductivity. Understood? So what is a molar conductivity? Molar conductivity can be defined as at a given concentration, if you consider the 1 mole of electrolyte which has been dissolved in a solution, how much of the ions which has been produced from this 1 mole of an electrolyte, that is said to be a molar conductivity. Understood? It is defined as the conductance is due to all the ions which has been produced by dissolving only 1 mole of an electrolyte. That is known as molar conductivity. And we can write the molar conductivity in terms of lambda m, or you can say it is also represented as inverted Vm. Usually we call it as a lambda m, or you can say inverted Vm. Okay. So lambda m, which is directly proportional to the, what is this? Kappa. That is nothing but a specific conductivity, or you can say it is a conductivity, right? So conductivity into V. What does the V represents? Here V represents the volume of the 1 mole of electrolyte. How much you dissolved electrolyte here? 1 mole of the electrolyte you are dissolving in a solution, so that the ions which is produced from this 1 mole, which are responsible for conducting the electricity, right? So that is why it is named as molar conductivity. The name itself shows that it is a molar. How much the mole? 1 mole of electrolyte you are dissolving in a solution. So how much of the ions which has been produced from that 1 mole, which are responsible for conducting the electricity or responsible for conducting the conductivity. So that is why we can write lambda m, which is equal to K into V, where K is nothing but a kappa, which is nothing but a conductivity, and V is a volume in liter, which consists of 1 mole of electrolyte. But I can write C is nothing but a concentration, which is equal to 1 divided by V, which is inversely proportional to the volume, right? So here I'll consider C as a concentrations of a solution in a mole per liter. So I can substitute the values of the V in the above equation. So I can write lambda m, which is directly equal to kappa into 1 by C. 1 by C, right? So you can interchange here. So if you multiply these two, you will get, or else you can say that is volume which is equal to 1 by C. That is the volume of a solution which is equal to, or inversely it is proportional to the concentration. So you can place the values of the V in the above equation. It will become K into 1 by C, or we can directly write lambda m, which is equal to K divided by C. Remember, C is a concentrations of 1 mole of electrolyte. Then in the above equation, K expressed in terms of Simon per meter. Why? We have already understood that the kappa, that is nothing but a conductivity or a specific conductance, can be expressed in terms of Simon per meter. And also the concentration we expressed in terms of mole per dm cube, right? Or mole per cubic meter. So that how to find out the unit for this molar conductivity? So it can be obtained by dividing the values, that is a Simon per meter divided by mole per meter cube. Mole per meter cube. So now if you divide 1 mole will be get cancelled. So you will get Simon meter square per mole. Simon meter square per mole. This is a SI unit of molar conductivity. This is how we can easily define the molar conductivity by taking the concentration instead of volume. Understood? So what is a molar conductivity? It is nothing but a conductance is due to all the ions which has been produced by taking 1 mole of electrolyte. So only 1 mole of electrolyte which are responsible for producing ions. These ions will be responsible for conducting the conductivity. So that is known as molar conductivity. And we have understood that molar conductivity can be represented by the inverse Vm or lambda m, which is equal to K into V, where K is a specific conductivity and V is a volume of the electrolyte. Okay. So I can write V is equal to 1 by C. Why? Because the volume which is inversely proportional to the concentration. So that above equation will become K divided by C. In order to find out the SI unit for the above equation, we know that the SI unit is Simon per meter, right? And for the concentration, it is a mole per cubic meter. So the meter, 1 meter and 1 meter will be get cancelled, and remaining is a SI unit for the molar conductivity. That is Simon meter square per mole. Next, So it may also noted that if I want to take a 1 mole in terms of meter cube, okay, then above equation can also written that a K into 1000 divided by M, or you can say a lambda M, which is equal to kappa into 1000 divided by M, where M is nothing but a molarity, which is nothing but a molarity of a electrolytic solution. This is how we can obtain the final equation by considering a 1 mole of cubic meter. 1 mole of cubic meter. So if you consider the 1 mole cubic meter, the entire equation will become K into 1000 divided by M. So this is a final equation we used to carry out, or we used to carry in the solving the numericals to find out the molar conductivity of a given solution. Hope you all understood. Remember, the molar conductivity, which is nothing but a conductivity, is due to all ions which is produced from the 1 mole of electrolyte. And we have understood that which is equal to K into V, where K is a kappa and V is a volume, or K is a specific conductance. And we know that volume is inversely proportional to the concentration, right? So if you substitute the values for the V in terms of first equation, you will get K divided by C. So how to find out the unit for this? We know the unit for the concentration and we know the unit for the K. So if you divide these two, you will get the unit for the lambda M, that is a molar conductivity. Suppose if I take the entire, that is, if I take 1 mole in terms of cubic meter, then the entire equations will become K into 1000 divided by M. So here I have shown you that K is, the 1000 will be expressed in terms of liter, or in maybe it present in a meter, and molarity, which is nothing but a mole divided by M, that is we expressed it, we used to express this. The entire equation can be written in the form where M is a molarity of the given solution. Hope you all understood with the what is a molar conductivity. Now we'll move on to the next one, that is equivalent conductivity, which is represented by lambda equi. Okay, how to define it? This is due to the conducting power of all the ions which has been produced when 1 gram equivalent of the electrolyte which has been dissolved in a Vm of solution, that is Vml of solution, which means to say that if you take a container which consists of an electrode, one will be act like an anode and another will be act like a cathode. So here you are dissolving 1 gram equivalent of electrolyte. How much you are dissolving here? So you are dissolving 1 gram equivalent of electrolyte in a solution. In which solution? The VML of solution, that is the volume will be according to you. So you can say that we are dissolving the 1 gram of an electrolyte in the given ml of solution. So that ions which has been produced from that 1 gram of electrolyte, so that will be responsible for conducting the electricity. Hence it is known as equivalent conductivity. So here also I have written the direct equation, that is lambda equivalent, which is equal to K into 1000 divided by N, because here we have considered the volume in terms of normality. Okay, so N is nothing but the normality, and the SI unit for this equivalent conductance is nothing but a per ohm centimeter square, or you can say mho centimeter square, or you can say Simon centimeter square. This is how we can easily define the molar conductivity and the equivalent conductivity. Remember, in the molar conductivity, we are dissolving the 1 mole of electrolyte in a solution. But here we are dissolving only 1 gram of electrolyte in a given volume of solution. So the differences you must know, and the SI unit also you must know, and which equation we are using to solve the problem also you must know. That is the final equation. For the equivalent conductivity, we are using this equation to find about the numericals. Okay. Next, we'll move on to the variations of a conductivity and a molar conductivity with a concentration. Let's see how the conductivity and the molar conductivity will be varies with the concentrations of the electrolyte. So first I'll go for the conductivity. Okay. So usually when we increase the dilutions, conductivity will be decreases. When we increase the dilution, conductivity will be decreases. Why? Suppose if you take a container which consists of an electrode which is connected to the positive and the negative terminals of the battery, and this is an electrolyte which is present in the solution. Okay. If you dilute this solution, what will happen? The ions will be get separated, and more you dilute, the conductivity will be reduced. Why the conductivity will be reduced? If you dilute the solution by adding a dilute solution for that, the ions or the concentrated electrolyte which has been present in the solutions, it will get diluted. If the ions are get diluted, obviously it never responds for conducting the electricity. So that is why the conductivity will be reduces or decrease when you increase the dilution. So this is because the conductivity of an electrolytic solution, which depends upon the nature of the ions in a unit volume of the solution. With increasing in the dilution, the number of ions per unit volume will be decreased. Suppose imagine here the 20 ions will be present. 20 anions and 20 cations will be present. Imagine like that, okay? If you dilute to this solution, what will happen? The ions will be get diluted. If the ions are get diluted, what will happen? It never responds for the conductivity, so that the conductivity will be get decreased. This will happens only in the conductivity. Okay. So this is only in terms of conductivity. So when you increase the dilution, conductivity will be decreased. Let's see with the molar conductivity of an electrolytic solution. So in case of molar conductivity of electrolytic solution, it always increases with the dilution. How? We know that in a molar conductivity, when we are talking, we use a strong electrolyte and a weak electrolyte, right? So in case of strong electrolyte, due to the inter-ionic distances between the ions, when you increase the dilution also, the ions will be get separated. Once the ions will be get separated, it will be responsible for conducting the electricity. That is why in case of molar conductivity, if you increase the dilution also, obviously conductivity will be increases. So this is actually says because the inter-ionic distances or the interaction will be decreases, so that it increases the dilution with increasing the conductivity. Suppose in this solution, imagine the ions will be in the form of like this, or they have a strong inter-ionic interaction. If you dilute to the solution, what will happen? The inter-ionic attractions will be break. So if the inter-ionic attraction, once it breaks, these ions will be get separated out and it will move towards the respective electrode because of electricity or applying. So this is how, if you increase the dilution also in the molar conductivity, especially in the strong electrolyte, it increases the molar conductivity. Next, we'll move on to the weak electrolyte. In terms of weak electrolyte, this will not taking place. That is, inter-ionic interaction, it never get decreased. Here, the dissociations will be taking place. That is, the degree of dissociations of the ions will be taking place. If the ions will be get dissociated more and more, what will happen? Obviously, the ions will be responsible for conducting the electricity or responsible for increasing the conductivity. So in the weak electrolyte also, due to the degree of dissociations, it increases the dilution, it increases the total volume of the ions in a solution. Obviously, the molar conductivity will be increased. So this is how the conductivity and the molar conductivity, it increases or it will be varies with the concentration. It will be varies with the concentration. Remember, when we talk about the conductivity, when you increase the dilution, what will happen? Conductivity will be reduces. But when we talk about the molar conductivity, if you increase the dilution also, then conductivity will be increased. Why it is increased? Because when we talk about the molar conductivity, we use two different kinds of electrolyte for that. One is a strong electrolyte and the one is a weak electrolyte. What happens in the strong electrolyte? We know that in the strong electrolyte, there is a stronger interionic interactions will be there, right? If you dilute to this electrolyte, what will happen? The interionic distance will be decreases and these ions will become more free so that it can responsible for conducting the electricity. Whereas in case of weak electrolyte, what will happen? For example, if you take the acetic acid, that is CH3COOH. So what will happen? It undergo dissociation and produces acetate ion plus H plus ion. If you dilute also, again it produces acetate ions and hydrogen ions. So, during the degree of dissociations of the ions, what will happen if you dilute the solution also, the ion formations will become more and more. If the ions are more in the solution means, there will be a more in the conductivity. That is why in case of weak electrolyte, because of the degree of dissociation of the ions is more, the conductivity will be more even though when you dilute the solution. So this is what actually says that how the concentrations will be varies in the conductivity as well as in the molar conductivity. Hope you are understood with this topic. Next, directly we will move on to the by taking only a strong electrolyte, how the concentration, how the variations will be taking place with the molar conductivity in a strong electrolyte. Let us discuss. So already we know that strong electrolyte means, for example, you can take KCl, which is a strong electrolyte which dissociated forms potassium ion and a chloride ion, right? So what happens in the strong electrolyte as we know? So in case of strong electrolyte, if you consider a solution which consists of strong electrolyte, okay. So here the electrodes are connected to positive and the negative terminals of the battery. If you consider the strong electrolyte, we know that in the strong electrolyte, the interactions between the ions, between positive and the negative ions will be more, right? The interactions between the ions are more. Suppose if you dilute the solution, what will happen? The interaction between these two ions will be decreased. Once the interaction between the ions, if it is decreased, obviously this ions will be moved towards the respective electrodes and responsible for increasing the conductivity. So this is what actually I want to say in the molar conductivity of a strong electrolyte. But what happens at infinite dilution? Let's see. So due to the interionic forces, the conducting ability of the ions will become less in a concentrated solution on dilution. Hence the ions are move far away from each other and the interionic forces will be decreased. As a result of this, molar conductivity will be increases with the dilution as I have explained with the diagram. But remember, at infinite dilution, we need to know what will happen to the strong electrolyte. Now we have understood with the dilution. So when the dilution increases means conductivity increases with the strong electrolyte. Why? Because of the a strong interionic distances or the interaction will be break, and this breakage will be responsible for the formations of the free ions, and this free ions will be easily conduct the electricity. Understood? We'll see with the infinite dilution. In case of infinite dilution, when the concentration approaches to zero, then the resulting maximum molar conductivity, which is known as limiting molar conductivity. So, when during the infinite dilution, the concentration will become zero. In such cases, we used to call the molar conductivity as limiting molar conductivity, and it is represented by the symbol called lambda m naught. Lambda m naught, that is the limiting molar conductivity. And the conductivity of an electrolytic solution and infinite solution, it is known as limiting molar conductivity. What is the limiting molar conductivity? It is mainly nothing but a conductivity at a infinite dilution. So, the conductivity of an electrolytic solution at infinite dilution, which is said to be a limiting molar conductivity. So, let us understand this by taking the graph. Here, you can see that I have plotted the graph by considering the molar conductivity versus concentration. Okay. So, if you plot the graph by considering the molar conductivity versus concentration at infinite dilution, what will happen? The concentrations will be approaches to zero. The concentrations will be approaches to zero. This is known as limiting molar conductivity. This is known as limiting molar conductivity, and it is represented as lambda m naught. So, the molar conductivity of a strong electrolyte will be decreased with the increase in the concentration with increasing in dilution. The variations of the molar conductivity conductance with the concentration can be studied with the Vidhyaashram equation, and is given by lambda m, which is equal to lambda m naught into AC into the half. Here, A is nothing but a constant and C is the concentrations of the electrolytic solution, and lambda m naught, which is nothing but a limiting molar conductivity, and lambda m, which is nothing but a molar conductivity. So, the entire graph can also understand by using Vidhyaashram equation. So, from this equation we can say that when you increase the dilution at a particular point, the concentration will become zero. That is known as a limiting molar conductivity, and it can be defined as the conductivity of an electrolytic solution at infinite dilution. Okay, that is known as limiting molar conductivity, and we get a graph like this. Okay, and if you plot this graph, you will get the negative values of the A. So, here it is nothing but a constant. This is how we can expect the variations of a molar conductivity in case of strong electrolyte. Okay, variations of the molar conductivity in the strong electrolyte. Remember, in case of strong electrolyte, because of the stronger interactions between the ions, it never responsible for conducting the electricity. But if you dilute the solution, what will happen? The interaction between the interionic elements, it will break that interaction, and ions will get separated, and these ions, once it become free, which are responsible for conducting the electricity. And also at infinite dilution, we have observed that the concentrations will become low. That is also known as limiting molar conductivity, and it is also defined as the conductivity of an electrolytic solution at infinite dilution. Hope you all understood with the graph along with the strong electrolyte. Let's see with the weak electrolyte. Already we have understood that in case of weak electrolyte, degree of dissociations will be taking place during the dilution. What is the degree of dissociations? For example, if you take acetic acid, that is CH3COH, which gives rise to acetate ion and H plus ion. right? If you dilute the solution, what will happen? Again, the acetic acid will be produces acetate ions and H plus ions, right? So, due to the degree of dissociations of the ion, if you dilute the solution also, more number of ions will be produced from the acetic acid, which are responsible for conducting the electricity, so that during the dilution also, the conductivity will be increased. But we need to understand what happens at the infinite dilution, right? For a weak electrolyte, the variations of the molar conductivity with the dilution can be explained on the basis of number of ions in the solution. And the number of ions will be furnished by the electrolyte in a solution, which depends upon the degree of dissociation. As I have explained, degree of dissociation means the process of producing the ions which is meant for the conducting the electricity. Okay? And with increasing the dilution, what happened? Due to the degree of dissociation, more number of ions will be produced. If more number of ions which is produced means obviously molar conductivity will be increased. But the limiting molar conductivity of a weak electrolyte at infinite dilution cannot be obtained by extrapolations of delta M or lambda M to a zero concentration, which means to say that at infinite dilution, here the concentration is never equal to zero. For example, if you take this graph, you can see that this is a graph for the weak electrolyte, that is CS3COOH, right? So for this graph, you can clearly understand when you equal the concentration to zero, the graph or the concentration of a weak electrolyte, it never mixes with the or it never matches with the molar conductivity. In such cases, the limiting molar conductivity cannot be expressed. But here, in case of strong electrolyte, we have observed that at infinite dilution, the concentrations will be equal to zero. But in case of weak electrolyte, at infinite dilution, the concentrations will be never equal to zero. So, if you plot the graph or if you extend the graph also, it will be go like this. The strong electrolyte along with the molar conductivity will be go like this. This shows that in case of weak electrolyte, we cannot express in terms of limiting molar conductivity. So what do? In such cases, we will go with the Koch's law of independent migrations of the ions. Why? Remember, in case of weak electrolyte, what will happen? Due to the degree of dissociations of the ion during the dilution, it produces more number of ions. These ions will be responsible for conducting the electricity. But when we talk about the infinite dilution, the concentration is never equal to zero. In such cases, what will happen? The concentrations of the weak electrolyte, it never becomes zero with the molar conductivity. So, if you extend the graph also, the concentration never equal to zero. In such cases, we cannot expect the limiting molar conductivity, right? That is why we are using another new terminology for that is a Koch's law of independent migrations of the ion. Let's see what is this a Koch's law of independent migrations of the ions now. Okay. So, the Koch was one of the scientists in the year 1874. In the year 1874, he formulated the a law of independent migrations of the ions. So, how did he frame the law? By considering or by studying the various electrolyte, he found that during the dissociations of the ion, during the degree of dissociations of the ions, each ions which is present in an electrolyte which are responsible for conducting the electricity. So, he found that in the year 1874, Koch was one of the scientists. He formulated a law of independent migrations of the ion. So, how did he found? He found out by considering the different various types of electrolyte. So, once he studied the various electrolyte, he come to the conclusion that the limiting molar conductivity of an electrolyte, it is mainly due to the presence of individual ions in the solution. It is due to the individual cations and anions which is present in the solution. For example, if I take a sodium chloride as an electrolyte, here I cannot expect the limiting molar conductivity as we expect in the strong electrolyte. That is why what he said, in case of this weak electrolyte, remember the dissociations of the ions or the limiting molar conductivity of the ions, which is nothing but the individual ions which has been produced from the each electrolyte, which is equal to the individual ions, it may be cations and anions which has been produced from the electrolyte. So here this law just states that the limiting molar conductivity of an electrolyte can be represented by the sum of the individual ions which has been produced in that solution. So instead of taking the ion, he says that it is the sum of individual ions which has been produced from an electrolyte. So that is why it is known as Koch law. Okay, and for example, if I take lambda naught for the sodium and a lambda naught for the chloride as a limiting molar conductivity of a sodium and a chloride ions respectively, then the limiting molar conductivity can be represented as lambda m of sodium chloride, which is equal to individual ions. In sodium chloride, we can say that sodium ions will be there and chloride ions will be there. Similarly, you can write for the acetic acid also, CH3COOH. So which are the ions in the acetic acid? We can say limiting molar conductivity is due to the acetate ion. Acetate ion plus limiting molar conductivity of the hydrogen ion. So here both the cations and anions which are responsible for conducting the electricity, hence it is known as limiting molar conductivity of a weak electrolyte. It was expressed by Koch law, hence it is known as Koch law of independent migrations of the ions. Hope you all understood with this equation and along with the definition. So after understanding what is Koch law, we'll see the applications of the Koch law. Okay, using this law, the degree of dissociation and the dissociation constant of a weak electrolyte for a type AB can be calculated by using this relationship. That is degree of dissociation which is directly proportional to the any concentration, which means to say that the lambda m, which is nothing but a what? Which is a molar conductivity, and lambda m naught, which is a limiting molar conductivity. So the dissociation constant K can be given by C into lambda m2 square divided by lambda m naught into lambda m naught minus lambda m. So the degree of dissociation for the weak electrolyte at any concentration can be obtained by this equation. And also in case of using lambda, that is a lambda m naught for the both weak and strong electrolyte can be calculated by considering the individual values of the lambda naught and also of the individual values of the lambda naught. If you consider, we can calculate the values for the Koch law. Hope you are understood with the weak and a strong electrolyte. Remember, if it is a weak electrolyte, we can consider this equation. If it is strong and weak electrolyte, we can count the number of ions which is contributed for the degree of dissociations of the ions. Hope you all understood. So, we'll see a numerical how to solve by studying this concepts. Okay. A 0.1 molar formic acid solution, when it is placed in between the two electrodes, each which are having 2.5 centimeter separated by 0.8 centimeter has a resistance of 6956 ohm and calculate the conductivity and the molar conductance of the solution. Here already they have given the values for the A, that is area they have given, and also they have given the distances between the two electrodes, that is the L, right? So this is the value for the L, that is 0.8, and values for the A is 2.5. A is nothing but the area of cross section, L is nothing but the distances between the two electrodes, and also they have given the resistance, that is R value they have given, that is 6,956 ohm. Now we need to calculate the conductivity and the molar conductance of a given solution. How to find out this? We know that the conductivity which is equal to L divided by A into 1 by R. We know the values for the L, that is 0.8 divided by a 2.5 centimeter square. So it has to be centimeter square. Okay. Into what is the values for the resistance? 6,956 ohm. So if you divide this and if you multiply with this, you will get 0.000046, or you can write it as a 4.6 into 10 power 5 Simon per centimeter. This is for the conductivity. They are also asking us to find about the molar conductivity or the molar conductance. How to find this? We know that molar conductance, which is equal to K into 1000 divided by M. And we know the values for the K as we obtained from this equation, right? So K into 1000 divided by M. What is the molarity of the given solution? That is 0.1, which is given at the beginning only. So if you substitute the values for the K here, that is 4.6 into 10 power 5 into 1000 divided by 0.1 molar. So here observe, the centimeter will be get cancelled. So it will become 0.468 centimeter square per mole. This is how you can easily solve the problem. Just you analyze the problem first. Okay. Just you have to analyze the problem, what they have given. Remember here, they have given the length between the two electrodes. A has given, that is the area of cross section. Resistance also they have given. Only thing is we need to calculate the conductivity and the molar conductance. What is the conductivity says that? Which is equal to length divided by A into 1 by R. Right? So length and A we know that, and R also we know that is the resistance. If you substitute this, you will get the value. And for the molar conductance also, just now we have discussed that K is which is equal to K into 1000 divided by M. Molarity only they have given in the problem. By substituting those values, you will get the conductance and the molar conductance of a given solution. This is how easily you can solve the numericals in the electrochemistry. By this, we have finished this topic, that is a molar conductivity, equivalent conductivity, and also with the variations of the conductivity and the molar conductivity with respect to the concentration. And also we studied about the Koch law. Hope you all understood. In the next session, we are going to discuss with the electrolytic cell and the electrolysis. Okay. By this, I like to say that electrochemistry, don't think that it is too toughest topic in the chemistry. It is very easy only when you understand the things properly. If you don't understand the meaning, what is there is actually, you never understand the electrochemistry, and it's very easy once you know the things. Okay, please try to understand. We will meet you in the next session. Till that, take care and be safe. Thank you.